Okay, good evening again, everybody. I don't know what's going on, but well, accidentally the live streaming was offline, but now I'm back online again. So hopefully you can see me clearly, I guess. Okay, it's working. Very good. Okay, now you can post any questions you like to me. Just ask me any questions. Start asking questions. Come on. Yeah, as you can see today, I update my devices for our live streaming, right? It saves more energy. How much? Well, it's hard to say. I mean, well, it probably is for free, right? So Apple company just sponsored this video. So Apple give me a free iPad and an Apple Pencil. But anyway, please ask questions, okay? Come on, why nobody asks question? Your internet kills me. Yeah, so do I. Wow, that's great. So Leslie Shen is asking, hi Tony, how to interpret standard deviation of the error term? Well, what about we wait for the first 5 minutes? So what is the time now? Okay, 8. So let's wait for 1 more minute for you fix your internet or whatsoever. And oh, I think my internet also get very slow. I don't know why. But anyway, it doesn't hurt. Oh gosh, you want me to show you install DAP in multiple linear regression? Okay, those are good questions. Oh. Okay, now it's 8. Let's start answering your questions. Okay, so first of all, I've seen that you want to ask how to interpret standard deviation of the error term. Okay, now let's start with our multiple linear regression. So in the multiple linear regression, with this model is actually y equal beta 0 plus beta 1 x1 plus beta 2 x2 blah 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 plus beta k xk, so k independent variables, plus epsilon. So this epsilon is usually called an error term. Now, how do we interpret this error term? Okay, so if you draw a diagram of the multiple linear regression model, it must be some scatter plots, not scatter plots, but some plots near a straight line. So I can draw a straight line over here. I'll change the color. So this is a straight line, okay? This is a straight line. And for the standard deviation of the error term, well, before I tell you what does the error term standard deviation mean, let me show you 2 different scenarios. So in another scenario, we also have many dots. We have a we have a straight line, right? And we have many observed points. But those observations looks like that. Right. Now, you tell me, which of those scenarios, number 1 and number 2, which one has a larger standard deviation on the error term and which one has a smaller standard deviation of the error term? So as we all know, the error term in this model must be the distance between any observations and the straight line, right? So if the distance from any observation from the straight line is very big, then this error term must have a very large what? Standard deviation, right? Okay. So when we interpret the standard error or the standard deviation of the error term, is usually give us some information about the precision of making a prediction, okay? Let's see. In this case, the standard error is very large, right? So if the standard error is very large, not very large. So whenever you're making a prediction, it won't be that far away from the expected value, right? So when you make a prediction, you can be very precise. So if you predict a value over here, and you can see the actual result probably just very close to your predicted results. However, if you make a prediction in this scenario, what do you expect? You expect extremely large errors in your prediction, right? So that's why I say the standard error of the error term actually measures the precision of making a prediction, okay? So the precision of making a prediction, all right? So hopefully I answered your question. So the larger the standard error, the less precise our prediction is, right? And the smaller the standard error, the more precise our prediction is. Are you happy with that? Okay, now let's look at some of your other, I just bought this one today and see if I can use it. So let's look at your questions. Another question is, hi Tony, I want to know, do we need to install DAP ourselves? If yes, could you show us? Well, thank you for your question, Autumn. I believe in your Canvas, you will have a very clear instruction on the installation of DAP, because I don't have a computer with me, so sorry, I can't do that for you. But don't worry, if you can't install DAP in a lab, you can let anybody know, like in your exam room. I believe Boris will be there. Okay, so how do we interpret LCL and UCL in multiple linear regression? Okay, that's a pretty nice question. I'm answering Raina Lee's question, okay? How to interpret LCL and UCL in multiple linear regression. So let's look at the LCL and UCL. So in our estimation Excel output, you have basically 3 parts. The first part is the summary output, right? You have R square, adjusted R square, multiple R whatsoever. And the second one is I think this new one, I can double tap it and it becomes eraser. Oh wow, oh my gosh, this is so great. Okay, anyway, so ANOVA. Oh, what? Okay, yes, ANOVA. So the second table is ANOVA table. So I believe you are talking about the estimation in the third table. So in the third table, you will be given the estimation of each beta hats, right? So you have beta 0 hat, beta 1 hat, beta 2 hat, and their standard error of those beta hats, right? So standard error, you have blah, blah, blah. And you also have t, blah, blah, blah. And you also have p-value, right? Blah, blah, blah. Now, you will see the LCL of the 95% interval and a UCL of the 95% interval. I guess you mean that, right? Are you talking about this interval or the interval of the prediction? Hopefully you are asking this one, okay? So this LCL and UCL 95% generally give you an idea of another way of finding out whether this beta hat is significantly different from 0 or not. So the rule here is, first of all, if this interval, if LCL and UCL includes 0, okay? So if this one includes 0, then we must observe a very small p-value. So the p-value here, so let's talk about, for example, this row, okay? So if this interval includes 0, the p-value must be less than 5%, okay? So when p-value less than 5%, it means this coefficient is significant or not. Not significant, right? Oh, sorry. Sorry, I mean greater than 5%, sorry. My bad. Greater than 5%. So in this way, we can say that this beta hat is not significant, right? Or this independent variable is not significant, any beta I, okay? So this is another way of judging whether or not a individual independent variable is significant or not. So again, if this interval does not include 0, then you probably know the p-value must be less than 5%, and the beta hat here is what? Significant. Okay, beta is significant. Hopefully this answers your question, okay? If you are asking another LCL or UCL, just let me know, all right? So let's look at other possible questions. So how to interpret? So Baby King, wow, Baby King, that's a very good name. Baby King is asking, hi Tony, I wonder when do we need to use CLT and when do I just assume X follow normal in end of chapter exercise 10.52 and grade 30, but the solution just assume X follow normal without applying CLT? Oh, that is a pretty good question. Assume the population normal without applying PLT n greater than 30. I think you are talking about another story, I guess. So let's go back and see central limit theorem. So the central limit theorem is basically telling us no matter how x, which is our population, okay? So if we assume x is our population, and it can be with any distribution, right? Any distribution. So as long as we have a big sample size, namely when n greater than 30, then we can approximate the sampling distribution of sample mean, right? So our conclusion is x bar can be approximated by a normal distribution, right? A normal distribution with a mean which is equal to the population mean and the variance equals sigma squared divided by n, right? So this is basically our central limit theorem, what central limit theorem is telling us. However, when we are applying the central limit theorem, things can be very different, especially when we're doing some estimation or hypothesis testing. Sometimes, not sometimes, but many times, the sigma square is unknown, right? So instead of if sigma square is unknown, instead of using n normal distribution as an approximation, or I should say approximately, right? Approximately. So instead of using normal as the approximation, when sigma square is unknown, what do we use? Do you remember? Every time when sigma is unknown, which distribution do we assume then for x bar? Great, t distribution, right? T distribution. So in here, if sigma is unknown, whether or not it's x bar or x1 bar minus x2 bar, we all assume them follows t distribution with some freedom, right? So one assumption of using t distribution when sigma square is unknown is actually to assume x follows normal distribution. Okay, I mean the population, right? The population x must follow a normal distribution in order for x bar to follow a t distribution. Even though n is greater than 30, we prefer, if you read your textbook carefully, so it's actually in your textbook. So if you read your textbook carefully, it says the population x can be not normal, but not that non-normal, okay? It should still, we'd better make it still symmetric and looks nice, okay? So it can be not that normal, probably like this, but still it better assume it's normal, the population, okay? So probably that's why in your textbook, you will see this kind of thing. So even though you have x bar follow t distribution, you still assume x follows a normal distribution, okay? But don't worry, this kind of stuff, I don't think in your exam it will test you on in this deep, okay? Not that deep, so don't worry about that. All right, let's see more of your chats. What else? Let's look at a question from Ina Hu, okay? Ina Hu is asking, hi Tony, when we write a simple linear regression or multiple linear regression model, should y and x be capitalized or either uppercase or lowercase will work? Wow, I believe you are studying very, very hard. Well, let's see, okay? Let's see. Probably I can just write here, right? Another and make it bigger. Okay, this is awesome. Wow, awesome. All right, so this is actually a very good question. Shall we use big Y or small y, or big X or small x? That's a pretty good question. Now here, well, I don't think your marker will care about the difference between small x, small y, big X, and big Y. But you better know the big letters or uppercase letters, okay? Uppercase letters usually stands for what? They usually stands for random variables, okay? Random variables, okay? And for random variables. And for lowercase letters, they are the observation of the random variables. I use RV for random variables, okay? Observations of random variables. So, if you want to write in big letters, my answer is both is okay, but you need to pay attention to some details. So if you want to write big letters, you simply write y equal beta 0 plus beta 1 x1 plus beta 2 x2 plus beta k xk plus epsilon, right? So this is one way of writing your multiple linear regression model. Now, another way of writing multiple linear regression model is using the lowercase values. So for the lowercase values, this stands for observations. So for observations, they have to have an order on the observations. So you have to write down yi equal beta 0 plus beta 1 x1 I, small x1 I plus beta 2 x2 I plus blah 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 plus beta k x small x xk I plus epsilon I. Okay, so you know what I mean? So for if it is a lowercase value, they usually use what? Usually stands for what is this? What is called observed value. So for observed value, they must have this kind of I over here. Okay, so don't forget the order, right? The order is always here. Okay, but if you use uppercase letters, you can directly use this kind of thing. Okay, without any orders over here. Okay. All right, so hopefully that will answer your question, okay? Okay, now, anything else? Yuan Feng is asking, hi Tony, what's the difference between confidence interval and prediction interval? Wow, that is a fantastic question. Now, the difference between confidence interval and prediction interval. Even though you are not be tested on probably calculation, but it's always good to know the interpretation of them. The difference between confidence interval and prediction interval. Let me drink a cup of water. Okay, so where am I? Whether I can make this larger? No, I can't. Oh, poor thing. But this looks fancy, right? Much more fancy than before. I just use paper, right? Okay. But anyway, yes. Oh, where is your question? Oh, between CI and PI. Okay, yeah, sorry. So, what are the differences between confidence interval and prediction interval? So, for example, we want to predict, let's think about your final exam marks, okay? And only have a regression with your mid-semester. So this is your final exam mark, Y, and let's create a simple linear regression model to make it easy, okay? So beta 1, x1. So x1 is your mid-semester mark, plus epsilon. Now, after some regression, calculation, estimation, you've got your y hat equal beta 0 plus beta 1, x1, beta hat plus epsilon, no epsilon, sorry. What am I thinking about? Okay, so this is your estimated equation. Now, you want to make prediction, right? So for a confidence interval, you are predicting for all students whose mid-semester get, for example, 65, okay? And what is the interval estimation? So what is the interval estimation of the average mark, okay? Of the average final mark of those students, okay? So all students who got a mid-semester exam 65, and you want to have an interval estimation of the average final mark. But for prediction interval, it is actually predicting a particular observation, okay? So for example, if we know Yuan Feng has got, well, I believe you get much more than 65, right? But let's suppose you only get 65. So Yuan Feng got 65. So what is the interval? So same thing, okay? What is the interval estimate of Yuan Feng's final mark, okay? But not average, but Yuan Feng's. So interval estimate of Yuan's final mark. Can you see the difference? So as we can see, for confidence interval, they are actually estimating the average of all the independent variables or observations have the same feature, right? But for prediction interval, it is actually predicting a particular observation, right? So you need to know for CI and PI, which one is wider and which one is narrower. Definitely PI is wider. Very good. You are very clever. Okay, so now if you read your slides carefully, you probably have noticed that the confidence interval formula looks like y hat plus or minus t and minus 2 something times sigma hat multiplied by 1 over n plus x minus x bar squared divided by sxx, probably something like that. But PI is a little bit different. The formula is y hat plus or minus t times the sigma hat square root of 1 plus 1 over n, and same thing, okay? 1 minus x square divided by sxx, whatever. But you can see this is, oh, gosh, this is so bad. X minus x bar sxx, okay? So this is basically PI, the difference between PI and CI. This one, because you are estimating a particular observation, it will be less precise. So you plus 1 over here to make it wider. And for CI, since you are estimating the average mark of all those students, so it will be narrower than the prediction interval. Are you happy with that? Okay, now let's look at more of your questions. 1 smaller, 2 larger. What is autumn meow? What is 1 smaller, 2 larger? What do you mean? Well, anyway, forget it. Jiaring Gu is asking, for confidence interval, when we estimate P1 minus P2, the result of the formula will be totally different when we use P1 hat minus P2 hat or P1 2 hat minus P2 hat. How can we know which population 1 and which one is population 2? You sure they are different? I think you will get the same thing, but only the sign is different, okay? So don't worry about that. If you get different results, you must have a wrong calculation, I guess. So for example, if you estimated, P1 hat minus P2 hat, and you construct a interval like 0.6 to 0.8, okay? So for example, this is your interval. It shouldn't be this, no hat, okay? If when you're estimating P1 minus P2, okay, 0.6 to 0.8, then when you estimate P2 minus P1, you must get a minus 0.8 to minus 0.6, okay? So they must be inverse to each other. I mean, with different signs, right? With each other. But anyway, hopefully you understand. If you still get a wrong answer, please go back and check your calculation. I believe they will get the same results, okay? Now, so Ziwei Meng is asking, hi Tony, can you explain what is prediction interval of y? Okay, I just explained it. Great. Leslie Shen asking, when calculating CI, whether x1 bar must be all positive? Well, I didn't attend the revision class, but I think it depends on the question, okay? So if, for example, if they ask you the difference between male and female, then you use the male minus female, right? If they're asking the difference between female and the male, then you use female minus male, right? So it actually has nothing to do with 1 minus 2 or 2 minus 1. It totally depends on how the question is asking. But when, as a marker before, I usually mark both of them correct, okay? Because the difference is, otherwise it is too obvious. So other than that, I will usually give you a mark when no matter it's male minus female or female minus male, okay? But when they talk about the difference between male and female, you'd better use male minus female, okay? Right, this is Leslie. Thank you for your Leslie Shen question. So YG at 826 is asking, hi Tony, sometimes the plot used to detect autocorrelation is the plot residual versus observation number, not time. Why? Does autocorrelation only exist in data collected over time? Yes, I think so. Well, if it is observation number, I believe this observation number is also observed based on a time frame, okay? Because autocorrelation usually only exists in the time series data, okay? So the order of the observation is also like a time series, right? You order the first one first, and second one second, third one third, fourth one fourth, right? So this is like a time series, right? So yes, it is. Leslie Shen is asking, do we need to write assumptions of hypothesizing if question is not required? No, then no. Just answer whatever you are asked, okay? So for Leslie Shen's question, oh, block. No, don't report. No, don't do that. Cancel. You don't need to write the assumptions if the question is not asking you, okay? Right. Tony, could you explain where does the degree freedom come from? It's hard to remember. Come on, what degree freedom are you talking about? We have so many degree freedoms in everywhere, right? But just remember them. If you apply more, you will remember them, so don't worry. But you can follow up a question like, how do I distinguish the ANOVA's degree freedom and linear regression's degree freedom, right? So Oliva, Zhang, if you want to ask that question, I probably can answer. So you can ask. But I will only answer you if you ask. So Lanaro1967 is asking Tony, if there is time, could you please show us how to calculate the test Sigfold regression coefficient? In particular, how to get the values for beta hat and beta without hat. Oh, come on. Well, so first of all, your question shows that you probably not so understand what is regression analysis is doing, okay? So in a linear regression model, as I wrote just now, in a linear regression model, we have y equal, for example, beta 0 plus beta 1 x1 plus beta k xk plus epsilon. And this is called a model, right? And when we're applying this model to do some estimation, we will get a estimated regression equation. So this equation is the one that with numbers and hats, okay? So it's y hat equal beta 0 hat plus beta 1 hat x1 blah, 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 plus beta k hat xk, and no epsilon, okay? So in your exam question, if you are asked, write down the multiple linear regression model, you should write down this one. But if you are asked, write down the estimated linear regression equation, you have to write down this one with all the numbers, plug in beta 0 hat, beta 1 hat, and beta k hat. And those numbers cannot, the calculation or the estimation of those numbers are not actually required in your final exam because it's a very complex optimization process. So basically, you have to minimize SSE by adjusting the value of beta 0 hat, beta 1 hat, and beta k hat. So literally, you are just doing for any sample of data. For example, this is a sample of data, okay? So in this sample of data, and you are actually finding the best line. So you're trying to adjust, okay? Adjust the position of the line by changing the values of beta 0 hats, beta 1 hats, and beta k hats, and try to find a line that minimizes SSE, which is the residual sum of square, okay? So in this way, when we get those numbers, to get the minimum value of SSE, we will fix that number. So in your Excel output, you are actually getting those beta hat numbers in this way, okay? So they are calculated in this way, and this is called ordinary least square method, okay? Ordinary least squared method, okay? Least means minimize, right? Square means the SSE. So ordinary means the traditional, right? Ordinary least square method. Okay, let's look at other questions. Rana Lee is asking, if we use p-value to answer question, do we need to write a test statistic before or just write a decision rule? Well, if you are asked to use p-value, then use p-value. If you're asked to use critical value, you use critical value, okay? So don't worry. It all depends on what the question is asking you. Leslie Shen is asking, would you explain trend analysis? What should we know about it? So trend analysis is all about time series data, right? So when you are talking about trend analysis, you are plotting some observed value against time. And this is what we call trend analysis. Nothing much, don't worry. What should you know about it? You should know what is trend analysis. That's enough. And probably you don't need to know what is trend analysis. You know what I mean? Yes, come on. Okay, Lanaro, well, whatever 1967. Also, could you please show us how to find the figures in the regression tables to make a quadratic regression equation? How to find the figures in regression tables to make a quadratic regression equation. What do you mean by make? Well, if we only look at figures, we cannot determine whether there exists a quadratic relationship. But instead, what we'll be looking at is the residual, okay? So if we observe a residual plot, which looks like this, okay? Then, for example, this is xi, and this is epsilon. So if you observe something like this, you probably need to consider whether y and xi has a quadratic relationship by adding up a xi square, okay, in your model. So simply by figures, we cannot tell, basically. Only look at the residuals can we determine whether to update our model to a quadratic one. Okay, so Oliva Zhang, finally, she's asking how to distinguish the degree freedom in ANOVA and not hypothesis testing, the regression analysis, okay? Because you can see in the ANOVA tables, right? In the ANOVA tables, when we talk about ANOVA model, we have, for example, SSR, right? We also have SSE and SST. And the degree freedom of them are, for SSR is K-1, and this is N-1, this is n minus k, right? So in ANOVA model, the model is actually y equal mu I plus epsilon, right? Mu I means the ith population mean, is that right? So in this model, k is the number of what? The number of treatments or the number of groups, right? So if we have k groups, instead of, now pay attention, I'm asking you a very hard question, okay? Now if we have k treatments together or k groups of data together, right? So this is group 1, group 2, group 3, and group k. So we have k groups of data. In order to estimate every single group population means, how many parameters do we need to estimate? How many? If we want to estimate each population means, how many parameters do we estimate? K parameters, right? So we have group mean mu1, we have mu2, we have mu3, and mu k. So basically, we have k estimations, right? So k estimations. So keep in mind, when we have k estimations in our model, the SSR's degree freedom is k minus 1, which is the number of estimation minus 1, okay? And SST is always the total sample size minus 1. So the total sample size is 1 plus 3 plus n1 plus n2, n3 to nk, so it's n plus 1. The SSE is simply SST's degree freedom minus SSR's degree freedom, which is n minus k, right? So this is in ANOVA model, okay? Now, if we are thinking about the multiple linear regression model, let's look at the degree freedom. So in multiple linear regression model, it's y equal beta 0, beta 1, x1 plus blah, 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 plus beta k, xk plus epsilon. Now, if we want to make an estimation on this model, how many parameters do we need to estimate? So k here defined as the number of what? Number of independent variables, right? So k here is the number of independent variables. So if k defined as the number of independent variables, how many parameters do we need to estimate? So from beta 1 to beta k, here we have k estimations, right? But don't forget, we have an intercept term, which is beta 0, right? Beta 0 is also something that we want to estimate. Therefore, in total, we have k plus 1 parameters to estimate, right? Which means we need to do k plus 1 estimations. Now, let's go back and see SSR, SSE, and SST, okay? And their degree freedoms. Since we have k plus 1 parameters to estimate, the degree freedom of SSR should also be the number of parameters to estimate minus 1, which is k plus 1 minus 1. Oh my god, it's k, right? And SST, again, n minus 1, I guess. So n minus 1. So SSE is n minus k minus 1. Hopefully, this can help you understand or remember some of the differences in the ANOVA model's degree freedom and your linear regression model degree freedoms, okay? Hopefully that helps. Now, let's look at any other questions. So Yuan Feng is asking, hi Tony, when should we use R square and when should we use just R square to measure the goodness of fit? I mean, for multiple linear regression, okay? So for multiple linear regression, when we talk about the goodness of fit, we usually use adjusted R square, okay? Because the adjusted R square has adjusted for the sample size and the number of independent variables. Otherwise, R square will always increase when you add on new independent variables, okay? So in multiple linear regression, we usually use adjusted R square. But R square still works. It still measures the goodness of fit, right? So it doesn't matter. That's not a serious problem, so don't worry. Sylvia Zhang is asking, hi Tony, I remember Boris mentioned that will only be tested on cases where sigma is unknown, but I'm not quite sure. Could you please make a clear statement? Well, I don't know what's going on in your final exam, but if Boris said that, I believe he will be right, okay? Because sigma is known, it's nonsense, it's unreasonable, right? Because we will never know sigma in a population, so don't worry. Clear statement. Okay, so you will only be tested on the cases where sigma is unknown, okay? So Maggie Wu, hi Tony, could you please explain the rejection region of Z and T for one-tail test and two-tail test? Do we need to calculate the p-value by ourselves in the exam? If you have Excel, you have to calculate that, right? So, rejection region. Well, okay, that's a good question. How do you survive the mid-semester? Oh, well, no, you didn't learn that in mid-semester, right? But anyway, let's talk about it. I was just kidding. I try to be mean, okay? Because I usually be too nice. Okay, now, Z test and T test, but whatever, no matter it is Z and T, it's symmetric, something like that, right? So if it is a right tail test, okay, so it's a right tail test, we will reject null hypothesis when our observed value of the test statistic, either the Z or T, I use T, right, and exceeds the critical value, right? So if let's try to use alpha equal 5%, so we will reject null hypothesis if the observed value of T, which is T0 or T observed value, which is what you calculate from your sample, okay? So T greater than the critical value, which is T alpha with n-1 degree of freedom, okay? I mean, only for mean. Well, in order not to, oh no. In order not to distract you or mislead you, I use degree of freedom over here, okay? Which means this is the critical value. Okay, so this is right tail test. So if it is a left tail test, so you will reject the null hypothesis when the observed value is less than your left critical value, right? So here we reject the null hypothesis if what? If your observed value is less than the minus T alpha with certain degree of freedom, okay? So this is the T alpha degree of freedom, minus T alpha degree. This is positive T alpha with certain degree of freedom. And this is your observation. This is your T observation, okay? All right. Now, again, how to calculate p-value. Sorry, I forgot to insert a p-value calculation here. So in order to calculate p-value, oh, no. I misclicked it. In order to have a p-value, you're actually calculating, let me change the color. You're actually calculating the probability to the right-hand side of your observed value of t, right? So to calculate p-value, your formula, so the p-value will be calculated by what? By what? By what? I'll just make it disappear. So p-value is calculated by your Excel code, right? So it's t dot what? T distribution, right? T dot dist. But for t dot dist, it usually give you the left-hand side probability, right? So you have to use 1 minus t dist with your observed value, the degree of freedom, and the cumulative, right? So this is how you calculate p-value using Excel. So some of you might ask, can we calculate this by hand? The answer is no. We can't calculate this by hand. So a very important note to yourself, we can never calculate this by hand. It can't be calculated by hand. Okay, so it can't be calculated by hand. All right, awesome. Let's come back. So let's go back to the left tail test, okay? The left tail test. So for the left tail test, how do we calculate the p-value? So again, the p-value stands for the probability to the left-hand side of your observed t. So your calculation will be the p-value equals the t dot dist, right? With your t observed value with degree freedom and 1. So this is pretty easy because it's asking you the left-tailed probability, right? Okay, so this is what is this? This is left tails. Now let's look at two-tailed case. So for two-tailed case, you will reject the null hypothesis either when your observed value exceeds the positive half an alpha with some degree freedom, right? Or less than this. This is t of half an alpha minus t half an alpha with some degree freedom. So either way, you will reject the null hypothesis. So if it is a two-tailed test, then you will reject the null hypothesis if what? If the absolute value of your observed value is greater than what? The t half an alpha, because those two parts add together should be the alpha, right? So each of side is half an alpha with a certain degree of freedom, okay? So this is how we determine whether to reject null hypothesis for two-tailed test. And the two-tailed p-value is actually the one-tailed p-value multiplied by 2. So basically, if you've got an observation that is positive, you not only calculate this probability, but also you calculate the negative of this value and the probability left-hand side. And we know that those two probabilities are equal to each other, then we just multiply it by 2, okay? So the p-value is just equal to 2 times the t dot distribution with t observed. Well, let's make it positive, okay? Make it positive. And then degree of freedom and 1. And if you make it positive, this formula will give you the left-hand side probability. So it's 2 multiplied by 1 minus this bad boy, okay? So 1 minus this bad boy. All right. So that's all about the decision rules and p-value calculations on the right tail test, left tail test, and do-tail test. Okay, hopefully it helps. Now, let's look at your chats. Maggie Wu is asking, or does you need to use DA or DAP? Oh my God, yes. You can also use data analysis or data analysis plus to have that, okay? Eranaro 1967 is saying, thank you for your previous 2 responses. I meant earlier, would we be required to write down quadratic or logarithmic regression equations model at all, or just simple MLR and SLR? Well, it's possible, right? I don't know, but you don't treat it as a disaster. I mean, a quadratic one. So for example, in your model, if you have an S square, you just treat it as another independent variable and write down the estimated equation as usual, right? So it doesn't make any difference. It's still linear regression model, so don't worry. Leslie Shen, how to interpret the coefficient of dummy variables? Wow, that's a fantastic question. Let's look at this. So, in terms of what is that? What are you talking about? What variables? Dummy variable. Yeah. If we have a dummy variable in your model and you estimate, for example, if you want to estimate salary, which equals something and plus an indicator variable which stands for the male and female. So one is male, female. Let's make it female, and 0 for male. Okay, 1 for female, 0 for male, and you probably have observed 4,000 over here. Okay, so when we interpret this 4,000, we can't say when the gender, right? So I, for example, is for gender. When gender increased by 1 and the salary increased by 4,000, oh my God, that is totally, absolutely idiot, right? Okay, now, what else? Yeah, so how should we do that? What do you think? How do we interpret 4,000? So when it is female, it's 4,000 more than male, right? So when we want to interpret this this coefficient, we usually say, well, as usual, we need to say keep all other independent variables constant, right? So keeping all other variables constant or unchanged. On average, so we need to say on average, the salary of female is what? $4,000 higher than that of a male, of males, whatever. Okay? Everyone happy with that? So this is the difference, right? It's more than what? Oh, the difference between female and male is 4,000. But don't forget, on average. So this one probably worth 1 mark, and keep all other variable constant, again, worth another mark, okay? Those are the 2 important things you need to mention in your answer, okay, in order to get full mark. All right, any other questions? Let's have a look at. Oh, sorry, I completely changed that. Oh, no, sorry, this is still new for me. So I'll just try it out and see if Silver John asking, does it mean that we will not be tested on the question which relative formula is not given in the formula sheet? Thanks. I think so. Well, but you'd better ask Boris to double check it, because I don't know what's going on in your final exam question, okay? But I think if formula is not there, but you still need to know some formulas that are not given in the formula sheet. So for example, you have to know 2 times 3 plus 2 equal 2 times 3 plus 2 times 2, right? So it probably also be tested, but it's not in your formula sheet, right? So who knows? Kexian Liu is asking, hi Tony, how to fill an ANOVA table if something is missing? Thank you, such as multiple R. Okay, so first of all, Kexian Liu, multiple R is not in ANOVA table. but I probably know what you are talking about. You're probably talking about the regression outputs, right? So for the regression outputs, in the first table, we have multiple r, right? So it's just the square root of r squared. So if r squared is something, it's just the square root of r squared. And you know r squared is SSR over SST. Well, it's all about the revision of formula. So you can just go back to your slides and see those formulas. I believe there's a very detailed table or slide introduce you where does each thing or each value come from in the Excel output. So you can just go back to your slides and see it. Okay, so a multiple r is square root of r squared. So if you know what is a multiple r, you know what is multiple r, right? Yes. Okay, let's look at other questions. Hopefully I didn't freak you out. Now, keeping values unchanged, the value expected to increase, the units increase, no on average required. Well, expected. So is expected equal to on average, right? So on average means is expected, because expect is on average, right? Expected to do what it's on average to. Okay, so same thing. Leslie Shen is asking, what has to be expected to rather than will increase, and do we need to write this for all interpretations? Yes, we do need, because it's never will increase, right? Can we say that, for example, well, let me have a new piece of paper. So actually, what we are estimating is the average of y, which is y hat, right? But you can see the actual y's are either higher than y hat and lower than y hat, right? But our estimation is based on y hat, so beta 0 hat, beta 1 hat, x1 blah 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 plus beta k hat xk, right? So for example, when x1 increased by 1 unit, the y hat will increase by beta 1 hat unit, right? But it's y hat will increase, but not y will increase, right? So y hat is the average of y. So it's the average of y given a value of x, okay? So that's why we say on average, or expected, because it's EY given any x, okay? So expected or on average, so same thing, all right? So that's why we say expected, no, on average, but never to will increase, because the true y's, you will never know the value of true y because of some errors over here, right? Hopefully you understand. Ziri Leong is asking, hi Tony, could you please talk about the assumptions before conducting ANOVA? It states that random error follow normal distribution. That means we have to conduct a chi-square test on residual? Oh, wow. So Ziri Leong, if you are talking about ANOVA, we usually do not have residual, because in ANOVA model, we are testing whether several different population means are equal or not, right? So in the assumptions of ANOVA, like for normal distribution, we usually require the data to follow a normal distribution, because you can see the data is constructed under ANOVA assumption is constructed by mu I plus epsilon. So we really require epsilon follows a normal distribution. But actually, when we plus something, a constant number, it becomes y, right? So we can also have y to be normally distributed. That's why before we do a ANOVA test, we usually first test whether the group 1 follows normal distribution, group 2 follow normal distribution, or group 3 follow normal distribution using chi-square test of normality, right? Because we usually do not do residual analysis in ANOVA, because y and epsilon have the same distribution, but just the mean is different. Oh gosh. just the mean is different, right? So don't worry, you'll be fine. Okay. Leslie Shen, if multicollinearity exists, what is the consequence? So if multicollinearity exists, it means, for example, if x1 and x2 are in one of your model, you only have two independent variables, which are x1 and x2. So if x1 and x2 are correlated, then it's very likely that none of those coefficients are significant, right? So both of them are not significant. However, when you look at the F-test, the overall significance F-test, the F-test looks significant, right? So in this way, if that happens, it's very likely that x1 and x2 has multicollinearity problem, okay? And what is the consequence? Consequence is that your model is not good. You need to change your model, okay? Keisha Zhang, in the Excel, is the p-value in the regression is one side? How about the F? In the Excel, the p-value in the regression, well, we have different p-values in regression. So if you are talking about the overall significance F-test, it is one-tailed, which is a right tail. But when you are talking about the p-value for the individual significance t-test, they are two-tailed. Okay? So those p-value of the each independent variables, they are two-tailed. But for overall significance f, it's one-tailed, which is right tail. Okay, dokie. What else? Thank you very much, Tony. No worries, my pleasure. Thank you for your help. No worries, my pleasure. Ina Hu is asking, hi Tony, in multiple linear regression analysis, should we test multicollinearity with correlation matrix in the first step, or do it later in the test assumptions normality or no correlation? It doesn't matter, Ina Hu. It doesn't matter. You can do it anytime you like, but you'd better do it at the beginning, because when we have from my experience, okay, so the first thing when you have a sort of data is to plot them, right? After you're plotting all of them, you try to you can try to have a correlation matrix, okay? So but there's no one rule saying that you have to do the correlation first before you do what, you know what I mean? Okay, so that's my answer. Oh wow, it looks like we resolved all your questions. This is remarkable, awesome. And I think this one works much better than the paper. What do you guys think? Or you think it's less clear? No worries. Keisha Zhang is saying thanks. So you can see there are input lags between you and me, right? So sometimes I won't have a real-time response on your questions. I do apologize for that, but yes, okay. Oh wow, this double tap really works. Wow, great. Okay, thank you so much. No worries. Great, thank you. So if nobody has any question, I can just call it a day, and you guys, good luck in your final exams, and you will be fine. I mean, QBUS5002 students are renowned for, oh, we have one more question here. I do need to perform a test on the correlation coefficient between X and Y. Which statistical test should be used? test on correlation. Go to your lecture slides and go to the text on correlation. I think there must have something. So let's go to your simple linear regression, right? Linear regression 1, right? So this is your regression 1, and we can have your PPT. So this is your PPT. Okay, linear regression analysis 1. So if you look at coefficient of correlation, can I write something here? Probably no. But anyway, when you look at coefficient correlation, let's see, there is a test. Ah, it's over here. This is the very test you have to use when you're trying to do a hypothesis testing for P. Okay. So let's see if I can. No. Open with PowerPoint. Let's see if I can. Yes. View. Oh wow, this is awesome. Okay. Right. Yeah. You know what I mean. I'm not trying to show off, but I just bought it. Okay. So it's new to me, so I had to try how to use this. Okay, because I'm very old. Yes, but this is the test, the very test you need to use, okay? All right. Okay. We have much more questions coming up. Let's look at your questions, bad boys. Which of the following statements is correct? Type 2 error is probability rejecting H1 when H1 is correct. B. In practice, the probability of committing type 2 error is always assumed to be 0.025. So the B is definitely wrong because type 1 error, probability of type 1 error is alpha. So I can draw you a matrix of this kind of error. So we basically have two scenarios. So we have H-lin is true, H-lin is not true. And this is when we reject H0 or H-lin, H0, sorry. Oh gosh, I'm too tired. And this is do not reject null hypothesis, okay? So when H0 is true, when H0 is true, and we reject the null hypothesis, this is when we call a type 1 error. And the probability of a type 1 error is defined as alpha. And when H0 is not true, but we did not reject the null hypothesis, this is called a type 2 error. And the probability is beta. So we can see your question. A, type 2 error is the probability of reject H1 given H1 is correct. Well, this is absolutely wrong because we never talk about H1, right? We always talk about H0. So it's absolutely wrong. So B, in practice, the probability of committing a type 2 error is always 0.05. Type 2 error, no. The type 1 error is alpha. So type 1 error always assumed to be 0.05. So Maggie Wu, hi Tony, could you please explain a little about time series analysis? So in time series analysis, as I can show you with much confidence, you will basically be tested on the smoothing of the data. So don't worry, Boris told me time series will not be that heavily tested, okay? So for the time series, I believe you only need to do the smoothing of the data, right? So the smoothing of data, not you only need to know. If you have time, you can definitely read all those, and they are pretty straightforward, right? So, but if you don't have time, just read how to smooth the data, and it's very, very simple. It can be done by a primary school student, right? So don't worry, you will be fine, okay? Because if you want me to explain time series analysis, I had to spend a 3-hour lecture to explain this, right? So just read it. It's not that hard, okay? You have plenty of time till your exam, all right? So let's go back and see your questions. No more questions. Okay, now I will have wait you for last 3 minutes. If no more questions, I will call it a day, okay? So now it's 9:17, so let's wait till 9:20. At the same time, I can show you this magic thing. Look at this Apple Pencil. You have noticed it can, oh my God, it feels so good. Oh, wow. But I'm not advertising it. Do not buy it, okay? Don't buy it, don't buy it. I won't tell you Apple give this iPad to me for free. No such things. All right. Any other questions? I guess no. Okay, if none of you have any question, let's just call it an end. So finally, good luck to your exams, and don't worry. I don't think your final exam will be hard, as long as you work hard, right? So you work hard, exam not hard. If you do not work hard, then final exam question will be hard. Okay, so that's life, boys. All right, since nobody has any questions, I will finish today's live streaming. Okay, and I'm very happy to have everybody in our unit of study of this semester, and I'm very happy to teach some of you in my tutorial. So I wish not to see any of you next semester, which means you have to pass the unit. Okay, all right, thank you very much. Good night. I'll miss you. Okay.